Hi everyone. Today we'll be talking about how you can get more from less with quantification, aggregation, and stability information from microliters of sample with Uncle and Stunner. So this talk is all about the data you can squeeze from just a droplet of liquid. In this case, protein quantification, aggregation, and stability information on two platforms that each use less than 10 microliters of sample. So quantifying protein concentrations can feel like a bit of a dull activity. When all you're trying to do is get everything to the same concentration maybe, and all the systems all seem to be sort of slow, one at a time, only kind of accurate options. Thankfully, Stunner is none of that. Stunner combines two different technologies in one instrument for the first time to enable answers on quantification and aggregation all at once. 2 microliters of sample get the concentration of your protein samples while making sure that you're measuring monodispersed proteins, not a bunch of aggregates, and it's all done in a 96-well plate-based format. So with UV-Vis for concentration and DLS for sizing coming out of 2 microliters of sample, the question that's next asked is how exactly does the plate make all of this possible? So Stunner can measure proteins at high throughput and high concentration by using a microfluidic circuit with 2 fixed path lengths to cover a wide dynamic range from 0.03 to 275 OD. The unique microfluidic circuits molded into the Stunner plates create the fixed path lengths that mean you know exactly what you're measuring. And the independent circuits also ensure that there's no cross-contamination or evaporation. All you do is you add the 2 microliters of sample into the input well, and the microfluidic circuit does the rest. In this case, that means that the samples are drawn into the storage channel, where a sample can be left for up to 2 hours without worrying about evaporation. And then during a read, Stunner pumps the sample from the storage channel into the microcuvette. Stunner circuits have 2 microcuvettes in each circuit with a 0.1 and 0.7 millimeter path length. And those 2 different size microcuvettes make the wide dynamic range from 0.03 to 275 OD possible. With that great technology behind it, Stunner delivers amazing results. Accuracy within 2% and precision within 1% from 1 to 200 OD. Let's check out a few examples of exactly how great those results are. So here we have uracil and tryptophan, which are NIST standards used to show that our fixed path lengths are spot on. The idea is to measure known samples of tryptophan and uracil and ensure that your results match up to the NIST certified results for those 2 samples. For standard reference material, or SRM 2082, all of the absorbances measured in an octuplicate across each of 5 instruments of those uracil and tryptophan standards were all within 2% of the desired results. In fact, with the mean and median within 1.25%. For a more real-world example, we turn to a gold standard antibody, NIST reference material 8671, also more commonly known as NISTmab. In this case, all octuplicate measurements across the 5 tested instruments were within 1.25% of the 10 mg per mil reference concentration of NISTmab. Mean and median values of the 40 measurements were actually within 0.6% of the reference value. To look at Stunner's whole range, here we're looking at a dilution series of IgG and PBS. On the left, we can see the UV-Vis absorbance curves for the full dilution series, all nicely peaking at 280 nanometers. On the right, we've plotted concentration against A280, the absorbance at 280, and we see the results are nicely linear with an R squared of 0.9999, or 9s. Nice. If we use that A280 and the known extinction coefficient for that antibody, we can calculate concentration. So here we're plotting known concentration versus measured concentration by that method. A slope and an R squared very close to 1 tells us that the data is excellent. In the table on the right, we can see exactly how close our known and measured concentrations are to get a good sense of how good accuracy to within 2% and precision to within 1% really is. And if you want to show off this accuracy in your own lab, we offer the fundamentals. This is a set of certified tryptophan standards spanning an OD range from 20 to 225, which is equivalent to about 20 to 160 milligram per mil for IgG. Testing those standards with our fundamentals check application is an easy and quick look at the accuracy, precision, and linearity performance of all of our instruments. And Stunner is completely automation compatible too. So throughput should never again be a problem for protein quant or for DLS information. And lastly, if you love this assay upstream and you're ready to move it downstream, performance verification on Stunner meets with the US Pharmacopoeia, Chapter 857, and European Pharmacopoeia, Chapter 22225, standards on absorbance accuracy and precision, photometric linearity, wavelength accuracy and resolution, and stray light. So it's all very nicely easy to get your performance verification samples run on Stunner and have your reports ready for you. So that's how Stunner supplies speed, accuracy, and a little bit of fun and style to UV-Vis quantification of proteins. Next, that actually brings us to UNCLE, which is the multimodal, all-in-one biologic stability platform that has the right number of options to investigate and solve protein problems. This talk looks at a few examples of how UNCLE can give you options to solve biologic stability problems that require a bit of flexibility. So that means proteins and viruses for this case. Sometimes, as we all know, if you only look at things one way, it can be unclear exactly what you're looking at until you take a different approach and see what it is you have in front of you. So with that in mind, that's why we have UNCLE as a all-in-one multimodal stability platform built for biologics. It offers 3 different detection modes to answer all sorts of questions. On the fluorescence side of things, it uses 2 lasers to excite either label-free protein intrinsic fluorescence or a variety of dye-based fluorescence methods. With full spectrum fluorescence detection, UNCLE can pick up both kinds of signals. We'll be looking a little bit more at both full spectrum fluorescence and dye-based fluorescence with our protein and AAV examples. SLS is the scatter light from those 2 lasers, and it gives information on when aggregates form. Dynamic light scattering is DLS and allows for detailed measurements of size and size distribution of your sample. So these 3 detection methods can all be operated isothermally or at room temperature or across a heat ramp designed to thermally stress samples and see which ones can take the heat. So the unique features of this system all kind of come from the uni, which is where we get our small sample size and our ability to do intrinsic fluorescence and extrinsic dyes. So each uni is a set of 16 quartz cuvettes where you simply pipette the sample in there, and then it's sealed in this blue frame with silicone seals. Because it's an aluminum frame, the heat is nicely conducted to the sample, and the silicone seals mean that you don't have to worry about sample leakage or evaporation. Simply load that on the UNCLE, and you can test from 1 to 48 samples by running up to 3 unis at a time in a single run. So a little bit about how the UNCLE is going to work with protein fluorescence is it relies on the intrinsic fluorescence of the amino acids inside of the protein. So we'll excite these amino acids with our 266 nanometer UV laser, and then each of these fluorescent amino acids, tryptophan, tyrosine, and phenylalanine will then fluoresce, and the signal is picked up by UNCLE's full spectrum fluorescence detection. As proteins melt and unfold, changing the environment around these aromatic amino acids mean that their fluorescence signature changes. So here we have an example of what exactly that change looks like. In this case, we're seeing over a heat ramp as UNCLE excites and reads the full spectrum fluorescence of a protein sample at numerous temperatures. Each line in this graph is a fluorescence read excited by that 266 nanometer laser, starting with the read at 15 degrees Celsius and going all the way up to 95 degrees Celsius. You can see by following the curves from top to bottom how they shift to the right side of the graph, which are the longer and redder wavelengths. This phenomenon is called a redshift and occurs because that protein's unfolding and tryptophan residues are becoming more exposed to the aqueous environment. So if we measure that redshift by tracking the spectral center of mass, sort of the wavelength where the area on the left of that wavelength is equal to the area on the right of that wavelength, then we can really nicely get a lot of really valuable signal and understand how that protein is behaving and redshifting. In this case, we can get a result that looks something like this, where in blue, we have fluorescence studied by that BCM wavelength, that center of mass wavelength. So as the protein unfolds, it'll undergo inflection points in its curve, which are labeled here as melting temperature 1 and melting temperature 2. Now, one of the most powerful tools of UNCLE is actually pairing its intrinsic fluorescence with SLS data, since that SLS data is going to give you valuable information on when aggregation occurs. So in this case, we're actually seeing a protein example where we have a melting temperature event, but aggregation doesn't occur until melting temperature 2 when the SLS data starts to increase, which is indicative of protein aggregation causing increasing scattering in your sample. In this case, in terms of looking at real-world antibody data, those aggregation temperatures, where the onset is marked as a T-ag here in this graph, they can occur simultaneously with TM1 of an antibody, in this case adalimumab, or they can actually occur at a TM2, as shown in this case with trastuzumab, or they can occur before any TM, as shown with cetuximab here. So really, it's important to measure both of those phenomenon simultaneously to really get an idea of what behavior is going to be most relevant to your protein. And that's how with UNCLE you can screen many different formulation conditions across different protein constructs to understand both protein unfolding and protein aggregation behavior all at once. All right, so let's take a quick detour and look at a case study for how UNCLE's full spectrum fluorescence can help you both understand protein stability and troubleshoot more unexpected behavior. In this case, we're starting with a protein that actually has a known amount of tryptophan behaviors, tryptophan amino acids, and we're going to add an additional, tyrosine. We're going to add an additional tyrosine and see how the result comes out. So in this case, we're looking at the 1-tyrosine type of the protein, and then we're going to look at, which is shown in blue, and then if we add that second tyrosine in green, we get a completely different behavior. So on the left of the curve, left of the slide, we're looking at BCM. In this case, with 1-tyrosine, we actually see no shift by BCM, but when we add in the second tyrosine, we see a redshift behavior, which is interesting, but not that unusual. However, if we look at just a ratio for this protein, we see a very different behavior where we get a flat line for 2 tyrosines, but actually a blue shift, which is a decreasing behavior for the 1-tyrosine protein. So thankfully, we have full spectrum fluorescence. We can investigate a little bit more on what's the deal with this protein. In this case, the full spectrum fluorescence gives us some clues. So we were 2 surprises. The first one is in the native 1-tyrosine protein, again in blue at the top. We see actually a stronger tyrosine peak than with 2 tyrosines, which is highlighted by the green arrow on both graphs. The second surprise is that the 2-tyrosine protein actually does appear to show more of a redshift than the protein with 1 tyrosine, shown by the blue arrow. So if we take a look at the full spectrum behavior in a slightly different view, in kind of a 3-dimensional view, we can see a little bit more about what's going on. So the second tyrosine is actually not only quenching the signal, but we can see that a new degradation product is forming. So once again, shown by the green arrow, we see that lower tyrosine signal, even though we've added additional tyrosine. But now with the blue arrow, we see that additional sort of red shift present in our sample. So that's pretty interesting. It does form very late in the process, and it does also seem distinct from the tryptophan signal. So if we can go and just select that one full spectrum read from pretty late in the process, what we get is a result that looks like this, shown in green. So in this case, we have the 2-tyrosine mutant shown in green, and we've put a likely suspect that we've run on a different example overlaid next to it in yellow, which is a sample of just IgG and dityrosine. And we can see that the peaks of having a dityrosine compound present in this sample match up very, very nicely to our mysterious peak that we were seeing in our 2-tyrosine protein mutant. So in this case, we can have a really nice clue that dityrosine is what was causing this unusual behavior, which makes sense since we know that we've added more tyrosines to the sample. So with UNCLE, we're able to see that difference between the two samples, understand it, investigate it, and really ID what the probable cause is in terms of this dityrosine formation. Now, also with UNCLE's full spectrum fluorescence, we're able to look at dye-based fluorescence. So this can be usually excited with the 473 nanometer blue laser, or also oftentimes dyes can be excited with the 266 nanometer UV laser as well. In this case, we're going to look at a cyber gold fluorescent dye, which is going to be very sensitive to the presence of nucleic acid, where it will increase in fluorescence anytime there's nucleic acid present. So by doing this, we'll excite it with that 473 nanometer blue dye. We'll actually gather SLS data from that blue laser as well. And then the dye-based fluorescence will happen between 500 and 630 nanometers. So here we're actually looking at an AAV sample, and there are two different methods that AAV will degrade. The first is by typical protein unfolding and capsid disruption, which is not that unusual from a normal everyday protein. But the second lower pathway seen on this slide is actually as you heat up the sample, the DNA is ejected from the capsids, and then the fluorescence of cyber gold that increases, like we talked about in the previous slide. So if we look at how that cyber gold fluorescence behaves, shown here in green, we get an initial fluorescence read based on how much free DNA is present in the sample. And then there's a slight drop in fluorescence as the temperature heats up, which has a kind of a, cyber gold has a dependency on the temperature that it's being read at. And then kind of the headline of the experiment is starting around 50 degrees Celsius with an inflection point around 58 degrees Celsius as DNA is being released from the capsids, which is well before when we know that unfolding and aggregation occur based on intrinsic fluorescence experiments, but it's actually shown here at the same time by looking at the SLS data in blue. So with one experiment, we're able to look at the initial amount of DNA based on the starting fluorescence of cyber gold. We're able to identify when DNA ejection begins to occur based on the increase in cyber gold fluorescence, and we're able to identify when aggregation also occurs based on the increase in SLS sample. And that'll typically be very well aligned with when protein unfolding happens as well. So lastly, UNCLE's third detection method that I haven't talked about yet is dynamic light scattering, or DLS. Now what DLS is going to provide to you will be a highly sensitive read on data about your protein size and size distribution. So here we're looking at some example data of a monomeric sample in blue, a sample with some aggregation in green, and a sample with significant aggregation in yellow. So the x-axis is in a log scale, just to know. So here we can actually notice that the z-average diameter increases as additional aggregation is present, and the PDI also increases as the sample's distribution widens. That's a really easy read to get an idea of what kind of sample quality you have, and it's also done a lot of times on UNCLE experiments at the beginning of the experiment, so you understand if this is done on a monodispersed sample or if it's done on a sample that's already suffering from some aggregation. Now, on the UNCLE, since we have the ability to do a heat ramp, we can also look at that protein in a different way by looking at DLS data taken over a heat ramp. That again gives us the size and size distribution as the protein unfolds and or aggregates. In this case, we're looking at an antibody sample where the size distribution graphs at the bottom show how we can track DLS data over that temperature ramp and then analyze it for any of a handful of DLS parameters. They give us indications about the temperatures where things aggregate or exactly the specifics on what size they are as that temperature goes up. This is a nice way of looking at how size is changing with temperature and still lets you dive in to get the details for DLS from each of those data points. So that's a look at what you can get only on UNCLE. With fluorescence, you see everything and miss nothing. You can get a full story on your protein and investigate further when something weird is going on, and that will help you identify the cause. With SLS, you get static light scattering, and you also get benefits that we didn't talk about here in this presentation that help you look at protein-protein interaction with B22 or G22 assays. And with dynamic light scattering, you don't just check that your sample is well behaved and high quality, you can prove it by showing that there are no aggregations present and that everything is the size that it should be. So all of this is combined and only on Uncle. So with that, we invite you to see things from all angles, including your protein stability problems. And now I'll ask, what questions do you have for me?